Okay, perfect. Hello, everyone. Thanks for having me. It's really a pleasure and an honor to be here. Thanks especially to Frederick for the invitation. And also thanks for Uli for the great and inspirational talk. So what I want to discuss today is several methodological challenges that we have faced when trying to develop and implement AI in the ICU in the Netherlands. Maybe just a quick note about where I come from so that you see what I worry about and why. So I have a background as a philosopher of science and as a mathematician. And after my PhD, I joined this medtech company, Pacmed, which is busy trying to build decision support for the intensive care. And I've been leading the research team there for a few years, and recently I made a step back towards the university, especially the Amsterdam University Medical Center. And the starting point of this presentation is just the realization that healthcare is a space in which AI has not arrived in full force yet. So we see the first application coming in, but there is a lot of delay compared to other domains. And there's been some notable blunders. You may have heard of the troubles that Google had implementing the retina scan. I believe it was in Thailand. You may have heard of the problems that Epic, the electronic health record provider, had when they deployed their sepsis prediction model in the US, redefining the notion of epic fail. And what we want to, so this is the starting point of the presentation today. So from a research point of view, what can we do to overcome some of these barriers, to speed up the application of AI to healthcare? I think Uri just gave us a great example of what we should do. I'm going to touch on some other methodological challenges and some research that we have done with collaborators to address these challenges. This is a visual cue to say, for me, to say that this is a bird's eye talk. So I'm not going to focus on one specific paper. I'm going to touch several of them, some which are published, some which are in progress, to give you an idea of all the research open questions you have to face when you try to build something that then goes to the bedside. So concretely, what I'm going to do is I'm going to tell you a bit more about the tool we built to aid discharge decisions in intensive care. This is going to ground so my perspective. This is the reason why I had some sleepless nights in the last 5 years and what I've been worrying about. And this is also the reason why I tacked some of the questions you'll see now. So the first question is, how do we let clinicians engage with AI? And so this is some the problem of the subfield of explainable AI. In my experience, when you offer a recommendation or a suggestion to clinicians, they want to know, why is that? For what reason is this AI recommending this? And we want to give them the option to agree or disagree. Another problem that we've encountered in practice is data shift. So we see from medical data that data changes over time, but also just different sources produce data that is different. So how do we handle that? If we have something in production, meaning that is running in the hospital, how do you handle the fact that some data that arrives to the model might be different from what the model has been trained on? So this is sometimes called the problem of auto-distribution detection. And lastly, this is what, so I was very happy to have Uri go before me, so I don't have to introduce any of that. But the problem of how do we give actionable suggestions to clinicians? So there's a difference between giving a prediction and saying to a clinician, this patient has this chance of this bad outcome happening. They often go, okay, but then what do I do? And telling them this is the best action to take right now. And that's the realm of causal inference, as you just heard. So I'll mention some of the projects we have in Amsterdam, specific to the ICU. Okay, so starting from the top, these are some of the slides that some of you may have seen, by the way, if you were yesterday at the AI forum. Apologies for those. I think they're relevant, so I'm gonna still go through them. For those that are bored, you can just have 10 minutes on your phone or something. But what I want to argue here is that intensive care is a great starting place for AI development. And the reason is that you have a large amount of data per patient. So patients are highly monitored. They are connected to machines that sometimes even register minute by minute their parameters. And the decision the clinicians have to take can be very complicated. And they are exposed to a large amount of information. So they have a high cognitive workload to go through. So they might need support. And finally, the intensive care is a very costly department in the hospital. And there's a shortage of staff, as we heard from the first presentation this morning. But also, surgery patients have to go through the ICU before going to the general ward. So it's also a bottleneck in terms of operations and planning what happens in the hospital. So the idea, the first idea that we had was, let's try to help the ICU by improving capacity. By the way, is anybody here not familiar with the intensive care unit? Please raise your hand. Okay. I guess COVID solved that for us. So if we can prevent some readmissions, meaning we can prevent patients that are discharged from the ICU to come back, we can improve capacity. So leave more beds available for new patients. And the idea there would be to build an AI that helps with choosing what is the optimal moment for discharge for patients. So if everything goes well, hopefully we could reduce the readmission rate, the mortality rate, and here I mean mortality after discharge, not mortality in the ICU, and also reduce the length of stay in the ICU. This is the main cost driver for the ICU. So what this company has been working on is this tool called Pacmed Critical, which tries to predict these adverse outcomes after discharge, so readmission or mortality in this time window of 7 days. And the way this looks on the in the hospital is this is the department view where all the patients are listed. These are fake patients. Then there's a diagnose, so the reason for admission, and there's this probability of this outcome if they are discharged. And this is predicted with a machine learning model. And for patients that cannot be discharged because, for example, they are mechanical ventilation, as this icon suggests, then this outcome cannot be predicted. And there is also possibility to zoom in into patients and to see more information about them. So, for example, here you still have this patient, some basic information, the risk here. There's a history of the risk over the admission, so that the doctors can sort of try to see whether this is decreasing or not, if it's stable. And then there is a top 10 features that, according to the model, are contributing the most to this prediction, some color coding, or whether they are risk increasing or decreasing. And the idea here is really to try to allow the clinicians to reason whether this number makes sense to them or not. So this has been discussed at length with intensivists, which are the ICU clinicians. And but nonetheless, this is actually going to change, because we realized that after several months of having this running, they would like it a bit different. So this is not final. And I have just a couple of slides to pass the message. This is has been a very long process. So we started working on this in 2017. And actually the tool went live August 9th, 2022. So it was about 5 years. And we had to jump through all these hoops, C certification, model validation, technical implementation, and then planning a clinical validation, the discussion with the ethical board. So I've discussed many of these things yesterday, so I'm not gonna discuss all the clinical validation work. Last thing I want to say is that the kudos the credit for this work is actually of this big team, so it's not my work alone at all. Also, it takes a large team to do something like this. This is something that's in the theme of the learning hospital is relevant to mention, that if you want to really bring something to the bedside, at least from the industry point of view, you need a long time and a big team. That also means that when you start, you need to make this very clear with your investors, because otherwise it's going to be problematic.
Just one question.
Yeah.
Can you say something about the breakdown of this team? Who are they? Like, what are the roles here roughly?
Yeah. Oh, by the way, I can take questions anytime. So thanks for doing that. So please interrupt me, just like with Uri. So there are, of course, some founders. There is some clinicians from the ICU, legal staff, compliance, so people that work with the C certification process, research people like myself, and then there's a very big technical team, so engineers, data scientists, that actually build all the backend. The modeling itself is perhaps the smallest amount of work, but the connection to the infrastructure of the hospital, building the cloud service that will serve the prediction in real time, etc. That's the big one. And then there are front-end designers, there are UX researchers that do what Uri has been describing. So they go to the hospital, they look at the workflow, they understand, okay, they actually need what we are building, and they will use it in this meeting when they do this discussion. And actually, in this other hospital, it works differently, the workflow. So these are all things you have to keep in mind. I hope that answers somewhat to that. And then there are product managers and office managers.
Thank you.
Okay, so when you build something like this, what are the methodological problems you need to have an answer for? So one of them, as I mentioned, is how do we let people engage with the tools? So how do we get users to engage with the tool? And I want to mention 3 problems that I'm interested in and that I'm working on. So one is that we do not tailor our AI interfaces to the users, or not enough. I will come back to this. The second issue is that, well, I've said this already, but we must be able to let clinicians decide whether the advice is sensible or not, because these machines are not infallible. So we don't want them to just trust it blindly. And either we don't want them to have to make a binary decision of, do I always follow this policy or I never follow it? But it would be nice to give them the ability to discern when and when not to agree. And finally, this is also a big topic of conversation in the realm of explainable AI, because these explanations that we furnish should actually be reliable. Sometimes there is this issue of confirmation bias that we'll come back to shortly. So on the first point, so we developed a number of techniques in this explainable AI domain to explain what the AI does to the users, but we don't really ask the users that much what they want. So what we are doing in this direction is we just put together a survey to just do that. Ask clinicians what kind of explainability, what kind of explanations would you find most useful. So we have a survey up, and I encourage all the clinicians in the audience, if you feel like it, please let us know your thoughts. This is just the introduction page, and this is something that's been done in collaborations with colleagues from the Faculty of Business.
One question.
Yeah.
Do you include, is it in a broad sense explainability, so including interpretability, or is it just like explaining a black box more exactly?
So of course, designing a survey like this is not the trivial, because you have to decide exactly what are you measuring, and what are the options you're giving as a choice. So the target of this was, let's say, a first step in this direction was to distinguish between feature importance methods, counterfactual-based explanations, and rule-based explanations. So to see which of these three is perceived as most useful by clinicians and why. Also because we don't want to make a survey that lasts 2 hours. Clinicians are very busy, so we try to keep it within 15 minutes. And then you have to test one hypothesis, basically. But there is also space for feedback. So if you fill it in and you have thoughts, please just write it down. The other issue I mentioned is we want to allow clinicians to engage, but we also want to speak their language. So we tend to develop techniques in explainable AI with a bit of a computer science mindset. So we tell clinicians, here are vector of numbers that represents the importance of these features. Here are coefficients. Here is a heat map. But that's not really how clinicians think about their patients. So we would like to link to concepts that they use every day. So, for example, in the intensive care, they have this framework, which is called the ABCDE framework, which stands for airway, breathing, circulation, visibility, and exposure. And these are macro categories they use to decide whether the patient is doing well or not. So why don't we try to couch our explanations in this way? Why don't we tell them, okay, this is the level of risk because of the airway indicator is not doing well in this sense.
Can I briefly interrupt? In terms of interpretability, don't you really need to have an interpretability if you have any hopes of applying it, deploying it within the legal system? You do need that, don't you?
I think so. So you said in the legal system?
Yeah, if we're thinking about some steps forward beyond the clinical trials.
So there is this part of GDPR that says that you are supposed to be able to provide explanations. That, at least as far as I know, has caused a lot of confusion because it's not really clear how that is operationalized. So what does it mean in practice? Is a set of coefficients enough? Is something like this more desirable? So if you ask me, I think it's
the tree-based model, and it's explainable in the end, or do you have to?
Yeah, so there is a lot of conversation about that. If you have tree-based, one decision tree is usually considered explainable, but if I give you a decision tree with 5 million nodes, it's not going to be that easy to explain. So we need to. This is, I think, a challenge that is still open. We need to find a way to operationalize these definitions in a way that companies and hospitals can take a model and say, okay, from a legal standpoint, this thing is interpretable. We don't have that at the moment, at least as far as I know. We don't have it in the Netherlands. What the Dutch have done, the Minister of Health has put together a set of guidelines for what is considered responsible deployment of AI. I also participated in these discussions. That's still not enough, I would say, but at least gives a bit more indication, because right now, if you build some medical AI, you're a bit in the dark of what you're required to do and what you are not required to do.
So there is the AI Act that is coming out by EU, and it does not require that you explain, but it requires that you can reproduce the exact thing. So you need to keep your model version, the exact input, what you outputted, the structure of the machine, everything.
Okay, so thank you for this question. So to wrap up this slide, what I was trying to convey is that indeed we want to try to provide explanation that comply a bit more with the clinician way of reasoning. So for example, I'm working with the student on giving explanations that are based on medical archetypes that are relevant to the task that the AI is trying to solve. And then the problem of confirmation bias, as I mentioned before. So suppose you get an image like this, and you are trying to classify animals, and your AI tells you, okay, this is a dowitcher, and this is why the machine thinks that is the case. The red pixels are the ones that are most relevant according to the machine. You might look at this and think, okay, the machine is looking at the beak, so I know the dowitcher has a particular beak, so the machine has picked up on this. This makes sense. By the way, this is a documentation SHAP package you can find online. And then the question is this convincing? And why is it? So some people have noted that the fact that this cloud of pixel is highlighted and this makes sense to us doesn't mean that it's highlighted for the right reason. So this confirmation bias basically means that we tend to believe explanations that comply with our beliefs. So we buy it, but maybe it's not, maybe if you feed just a random noise image, you get the same thing. So there is this, many people have discussed this. This paper in particular, I think, puts it rather clearly. But the line of argument is, just to recap, we have no idea whether explanations of the machine means what we think it means. And what we risk to do is we project our beliefs into the machine, and we accept explanations that are actually ungrounded. So this post hoc local explanations, meaning explanations of this one output on this one example, are not reliable, and we should not use them in medical contexts and not suggest them in guidelines. There was quite a debate on this at the ML4H, which we probably have seen on this topic. So I would say the root of this problem is that there are these sub-symbolic representations. So this is a fancy way to say a vector of numbers or a matrix of numbers. And we as humans cannot read off what they mean. If I give you a matrix of numbers, you can look at it, but what does it actually mean? What is the machine learned in this square of numbers? Not clear. So we need to link that, to match that to a symbolic concept that we use and we know what it means. So I have a paper with some colleagues that just came out where we try to sort of formalize this, make this problem as clear as possible. So if you schematically draw this, basically you have this sub-symbolic representation and you have some interpretation of it or translation of it in our notions. And what we want is that these two match to the set of states of the world that generates these explanations are the same for which we would apply our concept. That's what we would like to happen. And so this is an example why it fails. If I give you this image of this dog and this heat map, you might look at this and think, oh, this model is predicting a dog, and because of this heat map, is looking at the muzzle of the dog. So it's picked up, the model is picked up on these features. So I have this, I make this translation. I think, okay, this is a dog's head. The model has learned. But then I do this semantic match exercise. I see that this random noise image also generates this heat map. And so this is not an image to which I would apply this notion. So there is no semantic match here. So this is, of course, a wild simplification of a cognitive linguistic process, but to us kind of puts the finger on the problem. So then the next step is, can we operationalize this semantic match test? Can we find a way to see when it happens and when it doesn't happen? So if you take a sample with a features and label, and you have your explanation methods, it's called M, that generates this explanation E. What you want to say is, okay, I formulate some hypothesis theta, and I want to see whether this theta matches this explanation E. So if you just put it back into this diagram, this will be the sub-symbolic representation, heat map, for example. And this will be my hypothesis. This is the model has picked up there is a dog's head. And now I want to match, I want to test whether this match is happening or not. So we have an archive paper if you want to look at this, and where we describe this framework, and now we are doing further work into we're actually running experiments to see whether we can make this work. So that was about explainable AI. So basically, the last point I wanted to make here is that what we would like to get is a place in which we can certify that the explanations mean what we think it means, and therefore we can use them with confidence.
Can I ask one question about that?
Of course.
So, conceivably, for most input examples, there are multiple explanations that could be given by humans, right? So there are, like, for the same, states of the world, we could come up with many explanations. Just like there are many ways that we could summarize one document into a short paragraph or something like that, right? So I was curious, maybe you can say something about how you examine those sets or those explanations.
Yeah, so here in this framework, we really start from this corner.
Okay.
So we start from having an explanation and a sample. And then we formulate a hypothesis on what this explanation has captured. And then we test whether they match.
Okay.
So we don't formulate hypotheses or explanations wildly. We start from a given one, from a XAI technique. And then we see whether we can match it, whether it corresponds to any of our concepts. There is a number of issues. Of course, an explanation might pick up on several different things. And then there's a problem of compositionality because maybe these things relate to each other. Maybe there's a problem of locality. Maybe it's just this part of the feature space that is irrelevant to not the rest. So these are all things we're trying to tease apart in the experiment to see whether we can actually make it work.
Thank you.
Okay. Please let me know if I am wildly over time at some point. So the problem of auto-distribution affection, what is it? Suppose you have your AI software implemented in a hospital, the ICU. And then your model at the beginning receives data that is similar to training data. So here is your literal black box. And then you get some patient data, you make some estimation, and all seems to be going dandy. And then at some point, you start receiving some data points that are rather different from training data. Let's say this patient has age 6,500. Now the issue is that the model has never seen data like this. And you've never tested the model on data that looks like that. So you don't have real confidence what the performance of the model will be on this data that is out of distribution. So you can't really rely on this output anymore. So another way of thinking about this is suppose you have a machine to make orange juice, and as long as you put in oranges, you know that what's coming out is orange juice. But if somebody throws in an apple, then the output is not what you expect. Now, maybe distinguishing apples from oranges is easy enough, but then if these are vectors of 60 features, it might not be so easy to realize that the patients you have now in front of you is different from the training data. So the users, the clinicians, may just not realize that this new patient is out of distribution for the model. So they are blind to this failure mode.
Wouldn't you hope one of the instruments is flashing a red light?
Yeah, exactly. Why don't we do that? That's next slide. That's what we want to build. So I'll get to that in a second. But what I want to say first is that there is really a lot of reasons why there can be this data shift in the medical context. So turning from oranges to apples in the metaphor. So the population can change. Maybe it gets older. Maybe there is a policy against smoke. Maybe the diet changes, many reasons. The care protocol can change. New medications are introduced. There may be some bugs in the code that you don't know about and then can cause the data to drift. Might be systematic human error. This is maybe a bit grim, but given what's happening in Ukraine, maybe it's not so crazy that there might be a third party that wants to mess with your healthcare system. Many reasons. So I think we can say with very high confidence that the healthcare data will change, and that when we build our machine learning, we tend to have this IID assumption that data is identically distributed, and we can say the assumption is false in reality. Okay, so how do we address this? So you can do at least a couple of things. One is you monitor data periodically. The problem with that is that, so let's say you look at the distributions, and at some point, if they're shifted, you throw in a red flag. The problem here is that for the distribution to change, a certain amount of different patients have to go through the system. So you might have to do a lot of errors before you realize that the distribution has changed. Well, another thing you can do is you can do monitoring in real time, what the gentleman was suggesting. So you, every time a new patient is given to the model, you have a system that checks, is this patient similar to training data, or is it out of distribution? And maybe this system is not perfect, but at least you can prevent some errors. So if your system is saying this patient is out of distribution, for example, you can abstain, as we said. So you can defer to the clinician. And then if you see that this is happening many times in practice, you can say, okay, we have a lot of out of distribution patients here. Maybe there is a change in the patient population. We have to retrain the model. And the two things are not exclusive, by the way. So you can do this and also do that. But this is the goal that we are trying to achieve.
Can I comment?
Yeah.
But I assume when you say that you're going to monitor the data, right? But there are other externals you can monitor also. For example, you can monitor the development of introduction of new national guidelines, for example. So an external that you can get from your clinicians, and also you probably need to monitor the reference values and methods that are made in diagnostics, for example, in clinical laboratories, and possibly in radiology, change of methods. So,
yeah,
and you could do that in your home hospital.
Yeah, this is an excellent point. I think staying close to the clinical practice and understanding what is changing is also very important, because this might point to the need of adjusting your system before the data is really affected by it. Arguably, there could be situations in which maybe there's a new legislative framework coming out, but nothing changes in the data. This is a theoretical possibility. So perhaps in that case, your model could still work. But I agree that you don't want to deploy and then sit in a dark room checking this metric and never talk to the clinicians again. I think you need to keep in touch with the clinical practice. So how do we do that? How do we? So this is what's called auto distribution detection. This monitoring in real time. How do we do that? So some people have suggested that using a model's uncertainty can be a good way. So if a model is very uncertain, then maybe this data point is out of distribution. This is a paper that has looked a bit into it. There is, I would argue, not really conclusive information in the literature. And especially there's a lack of tests on medical data and even less tests on structured data like electronic health records. So what we did with some collaborators is that we tried to fill in this gap. So we took this now overused public data sets, MIMIC and EICU, and we tested several combinations of models and uncertainty metrics. And what we did is we tried to simulate different ways in which you could have an auto-distribution data point coming in. So one way is that maybe there is some corruption in your system. And so some features are scaled up by some factors that you don't expect. Another example is then a new group of patients arrives in the healthcare center where your model is deployed. It could be people with the new conditions, say COVID. It could be people with different demographics. Maybe you deploy the model in a different continent, so there's a different ethnicity. And then we also looked at the possibility of just having data from a different source. So we used mimic data as auto distribution when we trained on EICU data and vice versa. So we used one as auto distribution for the others. This is also, in a way, a domain adaptation problem. So I'm not going to show you all the experiments. I'm just going to show you the first one. But you can, so this is the factor with which we scaled a feature. So this is the corruption that we add to the data point. And so if there's small corruption, you see that this is the ability of the model to distinguish a corrupted data point from a normal one. If it's about 50%, it means that is as good as chance. And if it goes up, it means the model is good at distinguishing. If it goes down, it means it's getting worse than chance. And so what we see is that actually a lot of models get worse when we add corruption, meaning that the more corrupt a data point is, the more they think it is in distribution, which is the exact opposite of what we want. In fact, common denominator of many of these is that these are certain kind of architecture of neural networks. So then we had also the other experiments, which I'm not showing you because of time, but the insight is that uncertainty estimation techniques essentially don't identify this auto distribution, even in obvious cases like this corruption example. And this group of models actually seems to do quite the opposite. Techniques that seems to work a little bit better are density estimation techniques, which also don't do great, but they don't seem to be so obviously bad. And perhaps like a quick intuition of why that is the case is shown with this toy example. So density estimation will basically try to estimate where the data is dense, and we'll use that as a proxy for auto distribution. So if your point falls in a part of the space where the data is dense, the model will say this is in distribution. If it falls maybe here in the corner where data is not dense, the model will say it's auto distribution. And here instead, we use the uncertainty of the model to say something's auto distribution. And as you can see, these kind of models, so they are trying to distinguish two classes, and they use the uncertainty in this distinction to flag auto distribution. But they generalize outside of the feature space. So if a point is over here, maybe they've never seen anything like that, but they're very sure about the classification into a red point. And so if you use that uncertainty to classify out of distribution, they will be extremely certain this is in distribution. So this is a little bit the gist of why we think we see this in experiments.
Is there a way to combine the two maybe?
Yeah, so some of the techniques we tried combine, in fact, some of these techniques. They don't seem to be doing that great either, but there's a direction many people are investigating. So this paper is actually rather old by now. It's 2020. If you're interested, all the experiments are described in detail there. So our next step was to, well, let's try to figure out why we see this in the experiment. So let's look at the theory behind it. Some of these neural networks have this severe overconfidence. We see that if we corrupt the feature a lot, they're still very certain. And if you see, so here we plotted certainty, and you can see there are these white areas. White means certain, and purple means uncertain. You can see there are these white areas extending out from the feature space. So that's what causes the problem. And this is, we argue, related to the fact that this ReLU network are piecewise affine functions, and they split the feature space into polytopes. I'm not going to go into these details, but yeah, so this is what we observe synthetic data, and we wanted to prove whether we can define a class of models for which this happens, and whether this happens to many uncertainty metrics. you have a question?
Yeah, so I was curious, and maybe this is kind of a too big topic, but so I'm an emergency physician, and there, of course, it's kind of interesting to think about these kind of out of distribution, because we have that a lot in the ED typically, and you get, for example, when COVID, but also other situations, I mean, mass casualties, etc. And there, when we kind of get this kind of new data, the way to kind of handle that is typically that you adjust the model, so we kind of think in new ways, we kind of triage in new ways, and we kind of adjust how we work. And that's kind of very different from what you're describing here, because here, if I understand you correctly, you kind of have a static model, and then you kind of think, well, what we're going to do with the outliers, instead of using the outliers as something to adjust the model.
So thank you for this question. The problem here is that machine learning models need data, right, to learn. And so if we have an unexpected event coming in, for example, COVID, then if you train your model on pre-COVID data, you're not really sure whether it will work on COVID patients. Actually, we had this very problem, and it didn't work very well. So one obvious solution would be, okay, just add COVID patients to the training data, retrain, but maybe at the beginning you don't have enough because maybe there isn't a lot of ICU COVID patients. So what do you do in the interim period in between when you have this old, outdated model and these new kind of patients, but not enough to retrain? So arguably, I would say you have to abstain from giving bad predictions on the new patients until you can be the new model that is confident enough that we has a good enough performance on these new patients. So humans are quicker to adapt, right? But machines need, at least right now, quite a lot of they're data hungry. So we need to have the volume of patients to be able to retrain them.
But wouldn't we need the opposite? Because I mean, like when COVID came, for example, we were the clinical discipline was very unsure of what to do initially. I mean, there more than any situation you could actually need machines because there was a lot of data available around the globe. So I'm thinking, you're saying abstain, and I get that, but at the same time, that's what we really need help.
Yeah. So good point. So I think this links with what Uri was saying, that so these are scenarios in which what you're describing are scenarios in which we don't have RCTs because it's a new condition, let's say. So there is not a lot of guidance on what to do. It would be great to have at least preliminary information of what we should do, and we can use observational data to some extent to do that. So we had the project on proning in the ICU that tried to do this with the nationwide COVID database that we helped to build before any RCT on proning means flipping a patient on their belly to help their respiration. So that's a scenario indeed in which machine learning, if you can put the data together and get in a big enough volume, you could perhaps use some machine learning to help. But again, you need enough data, right? So if you have a single hospital, maybe you have to wait a bit to get the volume. So either you have a nationwide action going on, or otherwise it might be difficult. Okay, so going back to the auto distribution, the problem we wanted to solve is, can we understand this behavior from a theoretical point of view? I'm going to skip all the technical part. I'm just going to jump to the results. So if some technical conditions on the network are met, we can show that no matter how you measure uncertainty, so if you use either of these 4 known metrics, if you scale a feature, so if you do this corruption exercise, then the uncertainty will stabilize. And this is not what you want.
Sorry, stabilize with respect to what?
So it reaches a fixed point in the limit.
Fixed limit of data, or?
No, in the limit of scaling. So if you take the feature, at some point the model will be extremely certain, for example, and will stay until extremely certain, no matter how far you scale it. And this holds for single networks, but also for ensembles, MC dropout, base by backprop, so different forms of Bayesian model averaging. And we have some experiments also on synthetic data in the paper, which is this one, which was at UAI 2021, I think. So this is basically saying there is this class of model that is really not suited for auto-distribution detection. So we maybe should not try to do that more. And so this left us with the question, okay, but we have this ICU problem, and what do we do in practice? So we try to write down some sensible guidelines for how to do that. So the problems you face are, okay, so you have, by definition, you have your training data where you develop the models, and these auto-distribution points you don't have, because they will come after you deploy. So how do you shield yourself against those? And if you build this auto-distribution detector, how do you medically validate it? How do you check with clinicians whether it makes sense? And then you want to be able to catch these auto-distribution points that come from all kinds of angles. So maybe some are corrupted one, some is just a new group of patients, COVID, whatever. So how do you avoid overfitting on this one specific group? And finally, okay, so now suppose you have built this and you flag this auto-distribution sample. What happens to the, so you say to the clinicians, okay, I abstain. This patient is too weird or too new. I don't know what to say. Is that all? Or can we help the clinicians a little bit more here? Arguably, so possible solution here is you give explainability for the auto-distribution detector. So you say this patient is strange because of these things. And then the clinician can say, oh, this viral pneumonia version I've never seen. Maybe I should look into that. Maybe it's a different variant. And then it turns out, okay, there are COVID patients in the ICU. So we wrote this paper where we tried to describe different variables influencing these OD detectors. We show how to create OD tests from available data. So you can do some smart use of exclusion criteria to build OD tests. Here, GDPR is a little bit your enemy because it says you have to have only the data you need for the problem. While if you have a little bit bigger data set, you will be able to build better OD tests. And then we also have ideas on how to validate OD detection with the interpretability tools. So you sit down with the clinician and you say, okay, here's my OD detector. It says that this patient is strange. Is this patient actually strange? And the clinician can look at the electronic health record and say, oh, actually, this patient, we thought it was a discharged patient, but actually, this patient is too sick to be discharged. So probably this patient was transferred to another hospital. And then you also realize whether the OD detection is making sense or not. You can also debug your own data processing pipeline, by the way, in this way. And then we to make this come to life a bit, we show a practical example on EHR data from Amsterdam. This is also in a GitHub repository. Hopefully people can use some of these tools in their own, on their own data and their own problems. Is this paper that came out last year.
Oh, could you stop it?
Yeah.
I think somebody was taking it.
Yes.
Sorry.
Thank you. You felt it.
Yeah, so maybe shortly here, we basically tried different density estimators on this Amsterdam data set. And we had a prediction of hospital readmission, which is very unbalanced. Because the problem here also is that we want to stress test this in a real world use case where we have unbalanced data, mixed type data, so continuous categorical variable, missing values. So it has to be the real deal where we have to see whether this works. So we tried a few candidates for density estimators, and we did different things. I'm not going to show all of them. They are in the paper, but here is just an example. So if we tried that, what I just mentioned. So we supposed this new wave of COVID patient came in, and then we tried to see, would the model pick it up? And so some models like normalizing flow seem to be doing quite well. Some others a little bit less. But this is something you can try. So if you have this data, we also try to see whether the model will pick up that the patients couldn't be discharged because it was on ventilation or dialysis. different things.
I have a question. So often deep learning methods aren't the best, right, for such data. So do you have any insight about like non-deep learning alternative methods?
Yeah, so this is a very good question and a bit very general one. So one thing that always comes to mind when I think about this is that so deep learning methods work very well on so-called unstructured data, right? So images, text, which is arguably more structured than structured data because they have this notion of neighborhood in images and proximity in text that you don't have in tabular data. Tabular data, if you shift the columns, nothing matters. So there's no topology there. And that may be one of the reasons why neural networks don't work very or do not outperform dramatically tree ensembles, for example. And so we tried both. So some non-deep learning methods as well as deep learning here to see whether we could see a difference. The problem is that many of these things don't scale very well with high dimensionality.
So would you say right now you trust in certain deep learning uncertainty methods more than non-deep learning uncertainty methods in the medical context?
Yeah, so right now I think what I would trust, if you would ask me to pick a model, I would say some of the latest variations on variational autoencoders, like what's called MVAE or HIVAE, so things that take into account categorical or data distributed not in a normal way, would be the method of choice, I would say. Thanks. So
just one question.
Yeah.
Are most of the methods you investigate they are model agnostic, so they basically look at patient characteristics rather than include what the model is doing for that patient, or do you include both? Thank
you for this question. So maybe one thing I didn't say very clearly, but it's good to remark, is that these density estimators, they are independent model from the model that is actually doing the real prediction.
So it's model agnostic.
It's just another, exactly. So you will have some model predicting whatever it is here, hospital readmission. And then you have another model predicting the outside distribution. There are models that try to do both things, which were part of the experiments I showed you at the beginning. But as arguably, they are trying to do two things that are pulling the cart in different directions. They're trying to this prediction, getting good at this prediction impairs them at getting good at auto distribution detection. So that's why we are more tending towards density estimators.
I believe you have chosen an excellent starting point for deploying a machine learning model with a discharge time as your endpoint. However, discharge time is also extremely dependent on extra patient factors. So I wonder, do you just collect patient data, or do you collect, for example, days of the week, external patients coming to the clinic, or which doctors are on service, and sick days in the staff and stuff like that?
So this is an excellent point. So we know that the discharge decision has a lot of is influenced by a lot of external factors. Availability in the ward is a very big one that wasn't mentioned, but also the other one you mentioned. These are not part of the electronic health records, right? So the model won't see these things. So it needs to be complemented by the knowledge of the clinicians that is sitting in the ward at that moment. And that's it at the end of the day. So in an ideal world, we would have all these things logged, but right now we don't.
Maybe in the future, our employers would do that.
It would be nice. Okay, so let me just round up this, and I have just a couple of slides on causal inference. So another thing that I already mentioned is that you can do this qualitative inspection of outliers with medical experts. So you can say you train your OD detectors, and then you run it on the training data, and then you see whether there is any point in the training data that is actually out of distribution. And then you can look at those with the clinician. For example, you can do a feature importance for out of distribution, and see with the clinician if that makes sense. So we found, as I said, patients that were actually, instead of discharged, they were transferred to other hospitals because of this. So what is next for auto-distribution detection? As I said, I would argue it's better to have a decent OD detector than nothing. We have some working solutions, and what is the best model seems to be rather case dependent. So there is really, I wouldn't say there isn't really an out-of-the-box solution that I would say you just use this. What we need to do, I think, more theoretical work to understand what classes of model are best suited for this. And there is people that are trying to do some certifiable or some guarantees on OD detection. And I think we have to extend our random tests. Perhaps some more thorough benchmarking or community challenges could be very useful. Okay, I'm going to leave it at this. I just want to mention a few things on causal inference. You now are all experts after Uzi's talk. What are we working on when it comes to the ICU? Two problems mainly. One, assessing treatment effects for treatments of dynamic length. I'm going to define what it is in a second. And estimating adverse side effects of medication. So what do I mean by dynamic length? So in ICU is a setting in which oftentimes patients get some treatments as long as needed, meaning that treatment starts if some conditions are met. For example, if you have a respiratory crisis, you get mechanical ventilation. And then there is no fixed duration for this. So it's not like antibiotics cycles that they tell you, okay, you're gonna get antibiotics for 5 days, do all the 5 days, and then you stop. This is not how it works. They just intubate you, and then they reassess periodically whether you need it or not. So on the fly, they decide how long this is going to be. And so the question here is how much is enough and how much is too much, because many of these treatments actually have potential side effects. So if you talk about mechanical ventilation, you can have infection because of mechanical ventilation. And the ICU is a place where a lot of these things happen. We mentioned mechanical ventilation, but also the admission to ICU itself, which arguably has this structure. You are admitted if you need this high level of care, and then every day they decide, do you still need it? And as long as you're good enough, as soon as you're good enough, you're sent to the general ward. Proning is another example, and there are many others. So what we are interested in understanding is every time you do this evaluation, it would be great to have treatment effect estimation. It tells you, okay, what if you continue? What if you stop? And maybe some of you that have a sharp eye have noticed that Pacmed is not doing this. So we are only saying what the risk is if you discharge, but we don't say what the risk is if you don't discharge, which is also something the clinicians want to know. So they say, okay, but what if I keep this patient another day? Is the risk going to go down or not? What's going to happen? So we have, in a way, you can say we have taken a causal inference problem and addressed it as a prediction problem, which is not a good approach, I would say. And one way to think about this is you have this decision to end or continue, and then you have the same decision again. So you have sort of a tree with an infinitely extending branch with an exit option. So we have a 3-year project funded on this topic, which is starting this spring, funded by European Union. So we will be looking into this. Hopefully will allow us to improve this ICU product that is now running. And the other issue we are very interested in is side effect of medication. So ICU is a place where clinicians first and foremost want to save your life. So they can be sometimes a bit heavy-handed with medications, even medications that have side effects. So for example, nephrotoxicity. And we oftentimes have RCTs about effect of medication on some outcomes, but not so much about what are the side effects. And so, for example, antibiotics in the ICU, some of them, there is a high suspicion they are nephrotoxics. And also here we have a project that started a few months ago exactly on this. Okay, so I'm wrapping up. I hope I'm okay with time. So we looked at a tool to aid discharge decision in the ICU. We talked about some problems in explainable AI and what we can do about it, the issue of auto-distribution detection, and also mentioned some causal inference problems in intensive care. These are the people that are working on it or will be working on it. So as I said, Pacmed has been building this tool. Explainable AI, we have a collaboration with different faculties at the university. Tabea is a PhD working on this. She put together the survey. Auto-distribution detection, Mohammed is going to start in the spring. Causal inference, we have some PhDs working on the problem. I think that was, I don't know, if any of these topics is of interest to you, we're happy to collaborate. So please do reach out. Yes.
Just one simple question. Why did you decide to investigate the methods to allow you to discharge decisions in the ICU and not admission decisions?
So we also had a look at the problem of helping with capacity by predicting how many people would need to be admitted to the intensive care and how much space there would be in the ward. So sort of an input-output kind of approach. That proved out to be not so easy. And so we have actually parked that. We actually did a project on that with the University of Utrecht, which is another city in the Netherlands. So that project has been parked because it proved very difficult and not so impactful. And the discharge decision was something that the clinicians in the ICU, so we co-developed this tool with the Amsterdam University Medical Center. So from 2017, the clinicians had told us this is something we find very difficult and we would like to be supported with. So that's why we focused on that.
All right, thanks everyone. So in the interest of time, I think you're going to have to find Giovanni up by the lunch and in the discussion session afterwards for more questions. But before that, let's thank Giovanni.